Hi folks, welcome to the third video in your 10.1 lecture series. And in this video, we're going to take a look at Taylor polynomials at zero. Okay, so Taylor polynomials at zero. Turns out what we were talking about in that last video where I was like, here are some polynomials and like, look at how the more terms we have, the closer it gets to our e to the x, which is our example. We can use Taylor polynomials to approximate a lot of different functions. And it can be a neat way to write them because even though it takes some work in making the Taylor polynomials, it saves us some work on the back end when we're trying to approximate things. So I've given you two definitions here. The first one is a Taylor polynomial at zero. So if your function has n derivatives, so we have to make sure we can take all the derivatives, then the nth degree Taylor polynomial for this function at x equals 0 is as follows, okay? So we have our a0 plus a1x plus a2x squared plus all the way through anxn. And, I think I've said this before, but mathematicians were kind of a lazy bunch. So instead of writing out like all these different ones, we can use this special notation over here. Okay, so let me annotate on this a little bit. This is our summation notation. And all it means is so this pointy E, this is sigma, okay? Some people call this sigma notation. But this sigma means that we're going to add. So anytime we see the sigma, we're thinking we're going to add. And we're adding from when k is 0 all the way up to n. So n gets to change, or k gets to change numbers. It could be 0, 1, 2, 3, up to 9 we did in that first video, or up to 8 we did in that first video, 2 for the other question. This is just a shorter way of writing, I'm going to add together a bunch of terms, okay? And it turns out that the nth derivative is going to equal the actual derivative, and then all these coefficients we can find using this. All right, k is just from 0 all the way to n. All right, now I've given you a second definition. This one is what we call the concise form. It just takes this bottom information and plugs it actually into there. So instead of a0, we have f of 0, okay? So this f of 0 is our a0, and our f prime of 0 is our a1. And our f double prime of 0 over 2 factorial is our a2, okay? So we're just putting in our coefficients right into the equation. So that's why we call it a concise form. We don't have two different lines for the same information. We just put it all into the equation. And then this would be our sigma notation that says the same thing, okay? So in this video, we're going to take a look at two examples. The first example is going to be example number 3, where we find a third degree Taylor polynomial at 0 for this function f of x equals square root of x plus 4. Okay. After that, we're going to use this third degree polynomial to approximate the square root of 5. Okay. So let's get started. Okay, so step number 1, we are going to find our derivatives. Okay, so we're just going to go back to what we know about derivatives, and we're just going to find some derivatives, okay? So f of x is x plus 4 to the 1/2 power. Right? Remember that the square root is the same thing as the 1/2 power. So now we're going to go ahead and find our first derivative. Okay. So I bring the power down, x plus 4 to the 1/2 minus 1, which gives me negative 1/2. And technically I'm multiplying by 1, which is the derivative of my inside function. Okay. All right, f double prime of x. I'm going to take this negative 1/2. I'm going to multiply it by the 1/2, and I get negative 1/4 of x plus 4 to the negative 3/2, because negative 1/2 minus 1 gets us negative 3/2. And I got to find one more because I'm looking for a third degree polynomial. All right, negative 1/4 times the negative 3/2 gives me a positive 3/8, x plus 4 to the minus 5/2. Okay. So I found my derivatives. I know I needed to find up to the third derivative because it says third degree polynomial. So if I asked you for the fifth degree polynomial, we would have to go to 5 derivatives. Okay, now once we find these derivatives, we're going to go ahead and evaluate at x equals 0. Okay. All right, so in other words, for each of these 4, everywhere I see an x, I'm going to put a 0. All right, so f of 0 is 0 plus 4 to the 1/2, which gives us 2. F prime of 0 is 1/2 times 0 plus 4 to the negative 1/2, and that should give us 1/4. F2, or I wrote double prime over here, but this double prime is the same as the 2. Okay, so F double prime at 0, negative 1/4, 0 plus 4 to the negative 3/2. And that should give me negative 1/32. And last one, f3 of 0 is 3/8 times 0 plus 4 to the negative 5/2. And if I calculate that out and keep it as a decimal, I'm going to get 3/2, or sorry, keep it as a fraction, I'm going to get 3/256. Okay? All right. So you see a problem that asks you to approximate. You're going to find as many derivatives as you need, and then you're going to evaluate them at 0 if it's a Taylor polynomial at 0. Okay. Now we're going to use all this information to find our coefficients. Okay. So keep in mind what we're finding is like f0, f prime, f double prime, but what we need to find to write our polynomial is the a sub 0, a sub 1, a sub 2, and a sub 3. Okay, so we're going to use this information to find our coefficients. Okay. So we know that A0, according to our formula above, is just our F0. Okay, so A0 equals F0, and so that's going to equal 2 for this question. Now we know that A1 is equal to, I didn't mean to write the 0 that way, I'm so sorry, F of 0, which is 2. Our A1 is our F prime of 0, which is 1/4. Okay, now to find the A2, let's look at our formula. A2 is going to be F double prime of 0 divided by 2 factorial. Okay, so F double prime of 0 over 2 factorial. This is the same thing as saying f double prime of x times 1/2 factorial. Okay, so when we're working with fractions, it can get a little like tough in the brain, but if you have a numerator, you can treat it as a constant in the front times whatever your denominator is, like times 1 over that denominator. Okay, so we got negative 1/32 times 1/2 factorial. And this gives me negative 1/64. And last but not least, A3 is going to be my third derivative at 0 over 3 factorial, which we can think about as f triple prime of 0 times 1 over 3 factorial. And what did we get for this? We got 3 over 256 times 1 over 3 factorial. And if we simplify this a little bit, we'll get 1 over 512. Okay? So not that these are more important than the other things we found, but our A0 is 2. Our A1 is 1/4. Our A2 is negative 1 over 64. A3 is 1 over 512. These are going to go in for our A0, our A1, our A2, and we'll have an A3 here because we're looking at a third degree polynomial. Okay? Okay, so step 4, we're going to write our polynomial. Okay, so P3 of x, that's how we know it's a third degree polynomial. P3 of x is going to equal A0 plus A1x plus A2x squared plus A3x cubed. And I'm going to plug in all the numbers that I just found. So we have P3 of x is 2 plus 1/4 x minus 1 over 64x squared plus 1 over 512x cubed. Okay, so all I did, and I know I used the same color for all of those, but everywhere I saw the A sub whatever, I plugged in the number that I found from step 3. Okay, so we're just like, whatever we found for A0, we put that in for A0. Whatever we found for A3, we put that in for A3. But all of these are coefficients for like x, x squared, x to the third. Okay. All right, now we've written our polynomial. That answers the first part. Find the third degree Taylor polynomial at 0 for f of x equals x plus 4. But now we want to use this to approximate the square root of 5, okay? So step 5, we're going to use this to approximate. Okay, so if I want to approximate the square root of 5, okay, so f of the square root of 5, but keep in mind our function is f of, our function is the square root of x plus 4. So like, what number are we plugging in for x? We're actually not plugging in square root of 5. To get square root of 5, I'm actually plugging in 1 for x. So I don't want to write square root of 5 there. I actually want to put a 1. So I know that when I plug in a 1 for x, that gets me approximating the square root of 5. Like square root of 5 is the output or the y value, okay? So really, my 1 is going in for the x. What that means is that our f of 1 can be approximated, we use a little squiggle there, can be approximated by P3 of 1, meaning I'm going to go back to this Taylor polynomial third degree, and everywhere I see an x, I'm going to put a 1. Okay, so that gives us 2 plus 1/4 minus 1 over 64 plus 1 over 512. Okay, now let's type this all into our calculator and see what we get. And we get about 2.2363281. Okay, now if you type square root of 5 into your calculator, you're going to get the first 3 decimal places to be exactly the same. Okay, Now, I know what I just said, which is if you type in square root of 5 into your calculator, like why didn't we just do that to start with? Because we're going to use these Taylor polynomials to approximate things that are maybe a little bit harder to even put into a calculator. Okay, so it does have a time and a place, I promise, but this is kind of how the process is going to go. Okay, we're going to find the derivatives, we're going to evaluate them at x equals 0, we're going to find the coefficients so that we can write our polynomial. Once we have our polynomial, if the question asks us to approximate, then we can use that to get a good approximation. Okay. All right, we're going to take a look at one more example in this video. And in this example, let's look at the directions. It says, find the nth degree Taylor polynomial at 0 for f of x equals e to the 2x. Okay. I am finding an nth degree Taylor polynomial. So it's a little bit different from example 3. Example 3 said take the third degree Taylor polynomial. Now what I want to do is let's rewind all the way back to the first video. I want to come up with something kind of like this. Like I need to be able to find patterns so that I can use that to write out my Taylor polynomial. Okay, so the name of the game here is all about simplifying cleverly so that we can see the patterns that exist. All right, so first steps first, let's find our derivatives. Okay, now it's not a certain number, but we're going to find enough so that we can find a pattern. All right, so f of x equals e to the 2x. Oh, what a great chain rule question. All right, this is not just x, it's 2x. I'm going to have to use chain rule every time I take a derivative. All right, so f prime of x is going to be 2e to the 2x, because I got to bring that 2 down because the derivative of 2x is 2, okay? f2 of x, my second derivative, it's going to be the 2e to the 2x, and then I'm going to have to multiply by the 2 again. So that's going to give me 2 times 2 e to the 2x. And f3 of x is going to be 2 times 2 times 2 e to the 2x. And maybe I can start to see these patterns. This is really 2 to the first e to the 2x. 2 to the second, e to the 2x, 2 to the third, e to the 2x, and this first one is technically 2 to the 0, e to the 2x, okay? Well, let's think about what this is helping us find. I bet if we wanted to find the 10th derivative, it would be 2 to the 10th, e to the 2x. Right? You don't have to do this step, like pick a random one, but for me, that helps me say, okay, I'm more confident in my pattern now. This means fn of x, any derivative I want is going to be 2 to the n e to the 2x. This is the pattern we're saying happens when we find all these derivatives, okay? Okay, well, to write a Taylor polynomial, we need to have the coefficients, all right? So now we're going to use these to find our coefficient. Okay, so we know that we know that A0 is the same of f of 0. So that is our e to the 0, which we know is 1, okay? We also know our A1 is our f prime of 0. So I'm going to take my first derivative, 2e, and I'm going to plug in 0 for x, and this is going to give me A1 as 2. Okay, A2. We know this is the second derivative at 0. divided by 2 factorial. So this is going to give me 2 squared over 2 factorial. And even though I could simplify this because I'm looking for patterns, I'm going to wait on simplifying. Okay. A3 is F3 of 0 over 3 factorial. So that's going to be 2 to the third over 3 factorial. Now let's use this to guess what we think our A10 is going to be. I bet it's going to be F10 of 0 over 10 factorial. So that'll be 2 to the 10th over 10 factorial. All right. I think this gives me enough confidence to say that my coefficients are going to be 2 to the n over n factorial. Okay? So what does this allow us to do? Let's go back to our concise definition for a moment. Now I get to write my summation, okay? So this is my a sub n x to the k. Or if we look at this one, which might be easier, this is our a sub k. That's what we have here is all of our coefficients, okay? So we're saying that our nth degree Taylor polynomial is going to equal a0 plus a1x plus a2x squared plus a3 x to the third plus, I'm going to keep going until I have 2 to the n over n factorial x to the n. Okay, this is the super long way to write it, but let's practice writing it with our summation notation. So this is going to be the sum from k equals 0 to n of 2 to the k over k factorial x to the k. All right? And look at you working with some super high level math over here, okay? We just take it step by step. We know it's a lot more letters than maybe we're used to, but we're gonna find those derivatives and then find those coefficients, okay? Now, come on back for the next video where we're gonna take a look at Taylor polynomials at A, and that just means that X might not always be 0, okay? All right, I'll see you back here.